Now let's talk about another form of the first order differential equations. It's called the Bernoulli equation. The Bernoulli equation comes in the form of y prime plus p of x y equal a function r of x y to the power of alpha. Now alpha is a constant. If alpha equals 0, then the equation is considered linear. And if alpha equal 1, the equation is considered separable. So you have the general form of the Bernoulli equation: y prime plus a function p of x y equal r of x y to the power of alpha. Alpha is a constant. Either it's 0, it can be any number. If it is 0, then the equation considered linear. It will become a linear differential equation. As we remember from before, linear differential equation comes in the form of y prime plus p of xy equal q of x. If alpha is 0, linear. If alpha is 1, that means this equation is separable. So let's say we have a y prime plus 1 over x y equal 3x squared multiplied by y to the power 3, or y cubed. Now we will start with identifying, going back to the general form of Bernoulli equation. So you want to identify the p of x and the r of x and the alpha. So these three variables need to be identified. How you identify them in your example or in the problem that you're trying to solve. Okay, in this case, 1 over x represents the p of x, and 3x squared represents the r of x, and alpha, which is the power of y to the right hand side of the equation, represents so the 3 represents the alpha. Now, just to be more convenient and more prepared to be able to solve it conveniently, we can say that p of x equal 1 over x and r of x equal 3x squared and alpha equal 3. 1696, Leibniz showed that if alpha doesn't equal 1, then the Bernoulli equation becomes a linear equation with a change of variable in the following form. Change of variable is nu equal y to the power of 1 minus alpha. So Leibniz was saying that if alpha doesn't equal 1, then the equation, the Bernoulli equation, becomes a regular linear differential equation with a change of variable of nu equal y to the power of 1 minus alpha. Now we're going back to our example in here. Now we want to represent the change of variable in a way that relates to our example. So in this case, nu equal, as we said, y to the power of 1 minus alpha, which we know that alpha equals 3. So let's change the color in here. So nu equal y to the power of 1 minus 3 equal y to the power of minus 2. And in the same manner, y, if we rearrange this equation, y will equal nu to the power of minus 1 over 2. Okay, now we know that. Let's keep that in mind. Now let's find the y prime of this equation so that we can substitute this variable to the main equation and help us in solving it. So y prime, so the derivative of y equal nu to the power of minus 1 over 2 gives you y prime, or y prime of x, equal minus 1 over 2 nu to the power of minus 3 over 2 multiplied by nu prime. Okay, now going back to our main differential equation, we can replace wherever we see the y prime, we replace it with this value. So the equation becomes minus 1 over 2 nu to the power of minus 3 over 2 multiplied by nu prime plus, go back in here, plus 1 over x multiplied by y, which is nu to the power of minus 1 over 2, the value in the box in here, right? This equals the right hand side of the original equation, 3x squared multiplied by nu to the power of minus 3 over 2. Now if we multiply both sides of the equation, so both sides of this equation, just for simplification, we can multiply both sides with minus 2 nu to the power of minus 3 over 2. Okay, doing that, now we have, the equation becomes in the following form. It will become nu prime minus 2 over x multiplied by nu equal minus 6 x squared. Equation, now this equation, let's call it equation A, is a linear, just in the standard form of a linear differential equation. So the standard form of a linear differential equation is, as we remember, y prime plus p of x multiplied by y equals q of x. Now again, we are solving, just we can assume it's a regular differential, just typical linear differential equation. Identify your p of x and identify your q of x and solve the equation in a normal way. But instead of representing the y prime, you are representing the nu prime in this case. Then you go backward in substitution based on your assumptions. So just let's do it in the old way. So we identify p of x in this case for equation A is minus 2 over x, and q of x equal minus c x squared. Now let's solve it using integration factor method. So solving the equation using the integrating factor, we need first to find the integrating factor. As we remember before, integrating factor can be found in the form of e to the power of p of x dx in this case e to the power of minus 2 over x dx, which equals e to the ln of x to the minus 2, which equals x to the minus 2. So this is our integrating factor. Multiplying equation A by the integrating factor, so multiply equation A by the integrating factor, which is x to the minus 2, gives you x to the minus 2 nu prime minus 2 x to the minus 3 nu equal minus 6. And this can be called A prime. Now, simplifying this equation, let's simplify equation A prime. It will give you x to the minus 2 multiplied by nu all prime. So x to the power minus 2 multiplied by nu prime, all of them are prime, equal minus 6. Now, after doing the integration for both sides, this will give you x to the power of minus 2 multiplied by nu equal minus 6 multiplied by x plus a constant c. And we can say that nu in this case would equal minus 6 x to the power of 3 plus cx squared, and that is the value of nu. But to solve our original equation, we don't need the value of nu. We need the value of y. So going back to our assumptions, we assumed that, I'll put it in here again, we assumed that y equal nu to the power of minus 1 over 2. Doing that, we can say that y of x equal 1 over the square root of nu, which equals 1 over the square root of c x squared minus 6 x to the power 3. And that's our final solution of the original equation.